For this video, I'm going to talk about some methods to enhance the optimization that we do when we're training neural networks. So the goal here is to learn some methods that help learning go faster. So we'll start with stochastic gradient descent. Computing the gradient of the cost function can be very expensive and time-consuming, especially if you have a very large data set. So say, especially if you have a huge data set, in particular a huge training set. Remember, the cost is evaluated, it's the expected loss over the whole data set. So if you have a total of capital D training samples, then computing your loss involves adding up over all of your samples. So y sub d, t sub d. So if you have 50,000 samples in your training set, that involves running all 50,000 through your network and then evaluating the loss over all of those just to get one total expected loss. So rather than compute the full gradient over your entire data set, we can try to get a cheaper estimate by computing the gradient from a random sampling. So to be more explicit about that, let gamma be a random sampling of the data set, and there will be a random sampling of B, capital B elements from the total. So gamma is a subset of this set of 1 to D. It's basically a subset of the indices. Okay, so then we can estimate our true loss, true expected loss. I'll write that here. The expected loss between y and t will be approximately equal to the expected loss between y tilde, t tilde. I'm not very good at writing tildes. Tilde, tilde. Which is 1 over b, not d. And let's say b equals 1 to capital B. The loss between y sub gamma sub b, t sub gamma sub b. So this gamma is a set of indices from the full set of indices. Okay, we refer to this set as a batch, the set of inputs. So y sub gamma 1, t gamma 1, y sub gamma sub 2, t sub gamma sub 2, and so on up to y sub gamma capital B, t sub gamma sub capital B. That's a set of capital B elements, and it's called a batch. So we use the estimate from this batch to update our weights and then choose subsequent batches from the remaining samples. This method is called stochastic gradient descent. It's stochastic because we are taking a random sampling, stochastic sampling from our training set to evaluate our gradient. So in that sense, it's just an estimate of the gradient. It's not the actual gradient, because the actual gradient would be if we added up all of our samples. So this is really the method that's used most often, stochastic gradient descent. In fact, even if they don't call it stochastic gradient descent, it's probably using the same idea as stochastic gradient descent. You might have seen in PyTorch SGD, stochastic gradient descent. Maybe I'll put it here, SGD. I think I'm writing close to my head. So even other methods that I'll talk about shortly, like momentum and atom and stuff like that, use stochastic gradient descent in the sense that they are estimating the gradient stochastically from a subset, a randomly chosen subset of our samples. Okay, joke break. I bought a new metal brush to wash the gross taste out of our water pitcher, but now the water tastes irony. Okay, let's move on to momentum. Momentum is the next method I'm going to talk about as a method to accelerate or aid in the optimization process. So consider a gradient descent optimization in these different situations, these different cases. So I'm showing here the level curves of the objective function. You can see the x here where we want to get to the minimum, but we're starting over here at this dot. Now, if I were to take a gradient descent step, the gradient is perpendicular to the level set curve, so it would be taking a step over, let's say over here. Now I'd land over here. Now I take another step perpendicular to the level set and I go over here. Another, go over here, and then over here. And you can see that it's going to do a lot of oscillations, and it will eventually work its way down into the sort of valley here, but it's doing a lot of jumping back and forth across the valley. Also, most of the motion is across the valley, when what we really need to go down the valley. So this type of oscillation can be inefficient, and it'd be better if we sort of spent more time going down the valley. So let me just say these are the level sets of the cost function. Okay, so this trajectory is not ideal. That's case one. Case two, similar sort of thing, except now we're starting over on this one side, and there's a shallow, sort of less preferred and higher local minimum on the left here. So using strict gradient descent, we would just move down here and we'd say, yay, done. But if you look at the side profile of this, it actually looks like this. And what we really want to do is get down in this low valley down here. And so how do we not get stuck here? Let me just complete the picture. What we really want is to move down here. Okay, so the optimization stops in the shallow local minimum, but we would prefer to get over the hump and into the deeper minimum. Okay, so a technique to improve our prospects in both of those situations is a method called momentum, which is good because this is the momentum section of the lecture. So thus far, we have been moving through parameter space by taking steps in the direction of the gradient. So at each step, we have our current, we have our new set of weights and biases, our new parameters, come from our old set with a step in the direction of the gradient. Okay, so in that sense, theta is our location in our parameter space, and we're moving or taking steps in the direction opposite the gradient. But what if instead of our gradient being used as taking steps in particular directions, what if instead of we thought of it as a force that pushes us around through parameter space? So let's do a little bit of physics. Recall from physics that if theta is our position, then we can start writing out some what are actually differential equations. The derivative of your position with respect to time is velocity. And the derivative of velocity with respect to time is acceleration. Okay, so solving, let's say we had these two differential equations we want to solve numerically using Euler's method. We would say we update our position using our old position plus delta t time step in the direction of our velocity, and we'll call this equation 1. And now we update our velocity as our old velocity plus a delta t step in the direction of our acceleration. Let me add something here. In a real physical model, we would have, we'd have 1 minus r. So this 1 minus r is saying that as you're moving around, there's something resisting you, like error resistance or friction or something like that. So I've included that here. R is the resistance from friction. Now this A here is the acceleration. When you're driving a car, that's actually pretty much the only thing you have control over. When you're driving a car, the gas pedal is acceleration. You're controlling acceleration. The brakes are controlling acceleration or deceleration. Even steering, you're actually controlling acceleration because as you're moving, when you turn the wheel, you're actually accelerating yourself. Okay, since the wheels don't slip so much, I guess you could make an argument. Well, the wheels are accelerating you, I guess. Anyway, I don't want to get too much into the minutia of that particular metaphor, but anyway, that's how how you would use Euler's method to update the velocity and the position based on acceleration. So we're going to ask the question, or we're going to say, we treat our error gradient as A. So our error gradient is going to be our acceleration, and we're going to integrate and gain velocity v and thus momentum. So through acceleration, we're going to gain velocity, and that velocity is going to push us around through parameter space. So in more words, it's like our weights are dictated by our location in parameter space. Our weights are our location, and we move around weight space accelerated by the error gradients. We build speed if we get a lot of acceleration in the same direction. In that sense, we gain momentum. So if we've got a couple axes here, theta 1 and theta 2, just a two-dimensional parameter space, we're somewhere here in our space, theta, or you might call it W because it's a connection, weights, and biases, whatever. And at any given time, we might have a particular velocity v. But if we have acceleration pushing us in this direction, let's say, it's going to cause our next position to be over here. Okay, and you can imagine as time goes on, we're going to follow some curve through this parameter space. So for each weight, now I'll use W. For each weight, Wij, we also calculate Vij. Also calculate Vij. Or, that looks like on, or in matrix form, for each W, and I can even say for a given layer, let's say, we also have to track the velocity or the momentum that is going to be used to change that. So VL is going to get 1 minus R VL from the previous time step plus eta times the gradient with respect to WL of the cost. Or as is commonly used, it's slightly different parameterization. VL gets beta times the previous VL plus the gradient. So this beta is basically a momentum term in the sense that the bigger beta is, the more of the velocity from the previous step we keep in this step. As beta gets smaller and smaller, then we're basically, that's like turning the R up. The resistance is being increased. And once R gets up to 1, basically we have no momentum at all. We stop as soon as we no longer have acceleration. Okay, so we're sort of integrating our error gradients and turning them into velocity. And then once we have our velocity, we're tracking that as time goes on. We use it to update our weights. So the weight WL is the weight from the previous time step minus kappa times velocity. Okay. So you might sometimes see it parameterized a bit differently. I put the learning rate kappa in the weight update equation. Sometimes the kappa is or an equivalent parameter is put up there, but I'm not going to do it that way. Why? Because when I look at PyTorch and the way they have implemented momentum, it's more like this. Okay. So not only does this method, so we have to add a variable now. We're not just tracking the weights, but we're tracking a parallel set of parameters that are velocities or momentums. Of course, momentum and velocity are related, right? Momentum, which is often represented by rho, is basically mass times velocity. So if as long as your mass is constant, then your velocity and your momentum are essentially the same thing. Okay, not only does it smooth out the oscillations, there are other types of momentum that do smooth out the oscillation more, but more importantly, it can help you get out of places where there's a very shallow, like maybe persistent but shallow gradient, like a very sort of steady but shallow slope in one direction. What it does is, like a ball, it starts to gain speed, right? And so it can help you in situations where you've got something like this. So I've tried to draw this so that there's a little bit of a slope here. If you just looked at the gradient by itself, it would take you a long time to finally get down into the steep part. But if you're integrating your acceleration, you're going to pick up speed. Now I just also have a quick, that link will take you to this fairly long blog post, not mine, but it's just an example of a number of different methods that all use various forms of momentum. So we're adding parameters now, so there are many more bells and whistles you can add here. You can get like higher order terms. So this is just short comparing some of the main ones. Eta grad, eta delta, RMS prop, these are all terms you might have seen thrown around if you've been playing with neural networks. So what we're seeing on the left here is a fairly complicated and challenging objective function or cost function. And you can see the different solutions, optimization solutions, moving throughout this parameter space and seeking out that minimum, which is where that star is. So stochastic gradient descent is the red one. You can see it's kind of just moving slowly because it's a fairly shallow gradient, so it's not got a lot of incentive to move. These other ones, the green one with momentum, kind of shoots across the valley, goes back and forth in this little thing on the far side, and then finally comes back. But you can see it's much more dynamic, moving much more quickly. And now these other ones, which I won't talk about, have other mixtures of momentum and dampening. So this image here on the right is kind of another view. You can see that it's at a saddle point. So the biggest gradient is up and down the two sides of the saddle point. But what you really want to do is settle in the bottom of the valley and work your way down the side of the saddle. You can see stochastic gradient descent looks like it never really makes its way out of there. Kind of goes back and forth but stays balanced. The momentum one does start to build up some speed and eventually kind of falls down the side. These other methods are even far more effective at sort of dampening this back and forth oscillation and instead integrating and building up momentum in the direction of the downhill part of the saddle. So this lecture was about the optimization enhancement methods of stochastic gradient descent, just estimating our gradients from a subset of our samples saves us a lot of time because you don't necessarily have to see all your samples to get a good estimate of your gradient. And momentum, a way of helping us move faster through places where the gradient is not very big. These two methods are typically used together